Hi everyone, we are back, and let's pull up our pen here. Oops. Let's go ahead and get this going. So we are back, and we are about to go through our Pset 4 solution videos. So let's go ahead and let's get started. So for the stress strain curve below, determine which material is the most stiff. So most stiff has the steepest slope. So looking at this, I definitely think that it's going to be our purple curve. So purple. Most brittle, that's going to be our blue because our strain at failure ends here. The most ductile, it's probably a tie between either purple or red. Most compliant, so the least stiff, that's definitely going to be our blue. Most tough, largest area under the curve, that's definitely purple. Most strong, well, what do you mean by strong? So if you're talking about yield strength, the largest yield strength will actually be the red. The largest ultimate tensile strength will be the purple, and the largest stress at failure will also be purple as well, because it's probably right about there. So there we go. We got it. So that's our first solutions. So our first problem done. If the previous uniaxial tests were done on cubes, so we're looking at cubes with a side length of 150 millimeters and a force, and we can go ahead and draw our coordinate system here. If a force of 150 megapascals, actually it shouldn't be a force, this should be stress. So we are going to make sure that before we post that assignment, we're going to redo that. So if a stress of 150 megapascals was applied, what would be the final side length that is aligned with the force? So basically, if I was to apply this in tension, so in the two direction, 150 megapascals, what would be the final length in the two direction? L2 final. And then what about L1 final, L3 final? What about the other two slides? You can assume the material is a metal. So we know that stress is equal to Young's modulus times strain in this particular scenario, and this would be the strain in the two direction. This would be the stress in the two direction as well. You'll know that this is not the correct notation per se, but we're a little bit ahead of ourselves here. Metal, so we know our Young's modulus is equal to 100 gigapascal. We also know that the strain will be the final length in 2 minus the initial length in 2 over the initial length in 2, which our initial length in 2 is equal to this. So let's go ahead and solve. So I'm going to pull up Mathematica so we can do some math. Go ahead. Wait for that a little bit. This is the exciting part. I'm being facetious, of course. It's not super exciting, but it is what it is. So we're almost there. There we go. So let's go ahead and solve. And actually, we can set that for example, we know that our strain in the two direction is equal to E2 final minus, and I'm going to actually define here, Young's modulus is equal to 100 times 10 to the 9th. Our sig2 is equal to 150 times 10 to the 6th. We can also say that our E2 initial is equal to 150 times 10 to the minus 3. E1 initial equals E2 initial. And we have E3 initial equals E1 initial. E2 is equal to EF minus E2I divided. So divided by E2I. We can copy the exact same thing here for this, for 3, 3, 3, 3, and then 1, 1, 1. There we go. We also know that our Poisson's ratio for a metal is equal to 0.3. So those are just kind of not remembered values, but values that we've already defined previously. And our Poisson's ratio is equal to minus, basically in this problem, it's the lateral contraction over the axial expansion. So the axial, basically along where the force is being applied, is going to be the strain of the two. And this will be the strain basically here, because this is extending, and this will be minus because we'll flip it over here. So nu is equal to 1 or 3, equal in this scenario. All right, so let's go ahead. Let's define all those. And then let's actually define nu as well. Nu is equal to 0.3. So now we have our definitions. So let's go ahead and solve. Let's solve where we have sig2 equals y times E2. And we can look at this. This would be our final dimension. Makes sense, it's larger. And then we can do the same thing here, except for this is going to be nu is equal to minus EI, or minus E1 divided by E2. E2 final. Except we can solve for E2 final. So I'm just going to define this value now. So E2F equals this. We've solved for that. And now we can look at the final dimension here and the final dimension for my 3 dimension. Those should be equal. They're smaller, makes sense because they should be contracting, and we've got it. Hi everyone, we are back, and so now we're going to get into our last problem, which is a bending problem. So we're dealing with polymer, so Young's modulus is going to be equal to 1 gigapascal. We know our equation for stress in a beam is going to be equal to minus m times y over I, where I is equal to bh cubed over 12 for a rectangular beam. We also know that this is going to be our length. This will be our width, which is b. This will be our thickness, which is h. And remember, this is going to be our neutral axis right down the center here, y equals 0 plus h over 2 minus h over 2, and we have x, y coordinate system like so. So let's get to, I'm going to actually quit the kernel here. Quit the kernel. I think we have some definitions here. I think we've got these all written down here, which is great. So now we want to figure out what's the stress at the support. So here, so our moment at the origin is going to be minus 50 times L over 5 minus 1 times 5L over 6. So we can calculate that. Let's bring this over. So we're going to get m naught is equal to minus 50 times L divided by 5 minus 1 times 5L divided by 6, and then sig equals minus m naught times, let's go to the top of the beam first, divided by I, and we see, oops, it's trying to kick me out. We see that this value is positive. Now, why is that? Well, when this beam bends, this part is elongating. So the top of my beam plus h over 2 is actually going to give me a value that should be in tension. And if I do minus h over 2, that's going to give me compression. So that's it. So that is your problem set 4 solutions. Thanks. We'll see you in the next video. Bye.